Earlier in this chapter, we talked about ionic bonds and covalent bonds. Ionic bonds are very strong and non-directional. Covalent bonds are even stronger and are very directional. But the Lewis structures don't tell us anything about the actual geometry. This geometry is based on how atomic orbitals overlap and how that overlap can be favorable. But a simpler model called valence shell electron pair repulsion, or VESPER for short, can give us correct geometries most of the time. There are all sorts of reasons that geometries are important. Many types of drug design use molecular geometry docking simulations to predict drugs that may target a particular enzyme. Reactivity in small molecules is also driven by geometries. Polarity of molecules can only be predicted if we know the geometry. And, as we'll see next chapter, geometry can give us an easy way to think about more complex models of bonding like hybrid orbitals and even molecular orbital theory. In order to apply VESPER, valence shell electron pair repulsion theory, we need to draw correct Lewis structures, and then we can use them to identify the number of groups of electrons on an atom. Groups would be things like lone pairs, single bonds, double bonds, or triple bonds. These groups of electrons will stay as far apart as possible, as all groups of electrons are negatively charged, and so the number of groups usually accurately predicts the molecular geometry. If there are only two groups of electrons on an atom, the geometry at that atom will place these groups in opposite directions from each other, 180 degrees apart. This conformation is called a linear conformation. It usually occurs when one group is a triple bond or both groups are double bonds. If there are three groups attached to an atom, usually occurring when one group is a double bond, the geometry that is at that atom is trigonal planar, and the groups are arranged at about 120 degrees from one another. And if there are four groups, the groups must now arrange in three dimensions, with each group at about 109 degrees from the others. This is a very common configuration and occurs often when all groups are in single bonds or lone pairs. Because it's in three dimensions, I included a space filling model so that you can see the relative spacing a little bit more clearly. You can think of the four groups coming off as two V's. The first coming off in one direction, and the other coming off in the exact opposite direction and flipped 90 degrees. Less like an X and more like a teeter-totter. Whenever we draw this three-dimensional configuration in two dimensions, we'll use a bold line that's wider at one end to indicate a bond coming toward us, and we'll use a dashed line to indicate a bond going away from us. We call that arrangement tetrahedral. Again, both linear and trigonal planar configurations can be drawn easily on two-dimensional paper, because they are one- and two-dimensional respectively. So linear atoms have their configurations drawn simply as lines, as shown here with carbon dioxide. Notice that only the carbon atom is linear. The oxygen atoms actually each have three groups attached and are therefore trigonal planar. Carbonate gives us an example where the central atom had trigonal planar configuration. When we draw it, we try to space everything as evenly as possible, but it's still drawn in only two dimensions. Tetrahedral atoms, as we discussed before, are three-dimensional, so we have special rules for how to draw them on paper. In the example of carbon tetrachloride, a dangerous but effective solvent, two chlorines are drawn with normal lines about 120 degrees apart. You can see one going up and to the left and the other going straight sideways to the right. These indicate the two chlorines that are in the plane of the paper. The other two chlorines are drawn at about 120 degrees from the first two, but one is with a wedge, a bold line with one end wider than the other to indicate that it's coming out of the paper, and the other is drawn as a dash to indicate that it's going into the paper. Notice that in this example, the chlorines haven't been drawn with their lone pairs. This is increasingly common as you continue on in chemistry, especially for atoms that are on the outside of a molecule. Lone pairs are often assumed as we get used to seeing atoms with a particular number of bonds. Leaving out the lone pairs makes it much easier for us to see the structure overall. All of the examples so far have had every group as either a single or double bond, but lone pairs can also be part of our group structure. However, we sometimes have lone pairs as part of an atom whose geometry that we are actually interested in. This is complicated by the fact that we often omit the lone pairs even though they push other groups away in the overall geometry. For this reason, we'll often talk about the geometry based on only the attached atomic groups, which requires special names. So for example, if we have a tetrahedral atom and there are two lone pairs, the two atoms are still forced to be at an angle. They are definitely not linear. We say that they're bent. We also use the same name for a trigonal planar atom that has just one lone pair. That's also bent. This is common with oxygen and sulfur. If a tetrahedral atom has only one lone pair, we'll call it pyramidal, since it looks like a pyramid. This is common with nitrogen and phosphorus. Just because one atom has a particular geometry doesn't mean that every atom does. Most molecules have different geometries for the atoms that they can contain. Even a simple molecule like the methanol shown has a bent geometry at the oxygen and a tetrahedral geometry at the carbon. If we do want to predict geometry of any atom, we must first always start with a valid Lewis structure. So for the example shown, we know that the pH3 phosphine has 8 total electrons, 5 from the phosphorus and 1 from each of the hydrogens. Since each bond gets 2 electrons, we use 6 to bond to the hydrogens, and the 2 left over are held only on the phosphorus to complete its octet, giving the Lewis structure as shown. That part's review. Now, we see that there are 4 groups in the phosphorus, 3 hydrogens and a lone pair. The phosphorus must be tetrahedral, but because one of those groups is a lone pair, we can also call it pyramidal if we're only referring to the atoms. Either way, we must draw it in 3 dimensions to accurately represent the geometry. The lone pair could replace any of the hydrogens, but I find it convenient to draw pyramidal structures with the lone pair in the plane of the paper. Usually I put it on the top. Pause and try to identify and draw the correct molecular geometries for the remaining formulas that are shown. Try also to apply a proper name to the geometry of the central atom. The first molecule, formaldehyde, has a Lewis structure and a molecular geometry that are pretty similar. Since the central atom has only 3 groups, 2 hydrogens singly bound and an oxygen that's doubly bound, the carbon is considered trigonal planar, and everything can be drawn evenly spaced in 2 planes. The next molecule, methane, has a Lewis structure with 4 groups attached, all hydrogens singly bound. When we draw methane, which is tetrahedral, it must be drawn in 3 dimensions, an example of which is shown. Hydrogen sulfide has a Lewis structure with 4 groups, 2 hydrogens and 2 lone pairs. The sulfur is tetrahedral, but if we only consider the atoms and not the lone pairs, the sulfur has a bent configuration. We can draw the atoms in 2 dimensions, even though the lone pairs will come out of the plane of the paper. The next molecule, dichloromethane or methylene chloride, has 4 groups attached to the central carbon. It needs to be drawn tetrahedral. Notice in my example, I didn't include the lone pairs on the chlorines. If they only have 1 bond, we generally aren't concerned with the geometry, so it's common to leave off those electrons. Finally, the azide ion is an ion with 3 possible resonance structures. The first is the most stable, and therefore the most important. It only has +1 or -1 formal charges. The bottom 2 resonance structures are less important because of the -2 charges in the structure. If we're talking about any of these structures, the central nitrogen has 2 groups attached and is therefore linear. Sometimes resonance structures will actually have different numbers of groups attached. The geometry will generally follow the resonance structure with the fewest groups attached, even if it's less stable. For example, if any of the resonance structures shows an atom as trigonal planar, the geometry tends to be trigonal planar. We'll talk more about that later. We tend to focus a lot on Vesper theory for molecules with 4 or fewer bonds, but it's possible to get 5, 6, or even more bonds when d orbitals are involved. This occurs in the 3rd row of the periodic table and beyond, particularly with phosphorus, sulfur, chlorine, and transition metals. If 5 groups are attached, we have 1 straight up and 1 straight down. We call these axial ligands, as in the axis of rotation for the Earth. We also have 3 orbitals that are arranged trigonal planar to each other and 90 degrees from the axial ligands, shown here in yellow. These are considered equatorial ligands, as in the Earth's equator. Overall, this geometry is called trigonal bipyramidal. For the two three-sided pyramids that are formed by connecting the atoms on the equator with the top atom and connecting the atoms on the equator with the bottom atom. When we have 6 groups attached, the molecule is considered octahedral. Every group is at 90 degrees from each other, but we still have a difference between the 2 axial groups, again shown in red, and the 4 equatorial groups. The overall shape of the attached atoms is regular and 8-sided. We call it an octahedron. And so we call the overall shape of this an octahedral geometry. For a quick summary of all of the different geometries and how they're drawn, figure 4.16 from your text is really helpful. Similarly, if you want to see how the geometries change with different amounts of lone pairs, figure 4.19 is really useful. Notice that there are shape identifiers for lone pairs on otherwise trigonal bipyramidal or octahedral molecules as well, the 5 and 6 electron region systems. On trigonal bipyramidal atoms, the 5 electron system, 4 from the bottom in the table, 1 lone pair gives a seesaw configuration for the atoms, 2 lone pairs give a T-shape, and 3 lone pairs give a linear configuration. In 5 group systems, the axial positions are filled with atoms first, and the equatorial positions are filled later. If we look at the octahedral overall configurations, the one with 6 electron regions, 1 lone pair would be a square pyramid. 2 lone pairs are a square planar configuration, 3 are a T-shape, and 4 lone pairs give a linear configuration. Notice that in 6 group atoms, the axial positions get the first 2 atoms when there are 2 or 3 atoms that are attached, like in the linear or T-shaped configurations. But for 4 or 5 atoms, the equatorial positions are fully filled first instead. All of these, from 2 electron regions all the way through 6 electron regions, are ideal configurations. In truth, lone pairs usually repel a little bit more than atoms, since their electrons spread out more. For this reason, the angles in an ideal case that is not symmetrical tends to be slightly higher than the actual angles between atoms. Now that we've talked about molecular geometries, I want to remind you that some bonds can actually carry a dipole. They can be more negative on one side and more positive on the other side. We use differences in electronegativity to talk about this for any given bond. It's easy to see for a molecule like hydrochloric acid that the whole molecule would become more charged on one side than the other, just as its bond is. But for more complicated molecules, we need to combine the geometry of the molecule with the polarity of its bonds. While individual bonds can be polar or not, completely independently of geometry, the entire molecule is only polar if it has polar bonds that are asymmetrical, not balanced. For example, here are 3 different methane molecules with different numbers of chlorine. Every one of the bonds in tetrachloromethane, the molecule shown on the left, carbon Cl4, CCl4, is polar, but because every chlorine is evenly spaced around the central atom in a tetrahedral configuration, the poles all cancel each other, and there's no net dipole in the molecule. If you want to try to visualize that and you're having difficulty seeing how all the poles cancel, you can think about how the poles happen in pairs and how those pairs combine. In the tetrachloromethane as shown, the 2 chlorines pointed to the right pull equal and opposite each other in the vertical axis. The one on top pulls just as much up as the one on bottom pulls down, so they cancel. They combine and pull towards the right. The 2 chlorines on the left don't have any vertical component, only components going left and components going either in or out of the paper. The components going in and out are just as much in and out as each other, and they cancel. But they combine to make a component that's pulling left exactly the same amount as the rightward pull of the other 2 chlorines. So overall, the pulls end up being completely balanced and the molecule has no dipole. Hopefully that helps to convince you that the pull in a tetrahedral molecule is balanced. If it doesn't, you might just have to trust me. The next example to the right is dichloromethane. It's also called methylene chloride. a common carcinogenic solvent that may have been used to decaffeinate your coffee, your tea, or dry clean your clothes if, that's something you're into. Anyway, dichloromethane doesn't have a net dipole because the rightward pole of the two chlorines is added to a rightward pole of the carbon on the two hydrogen atoms. Even though the vertical and in and out poles are canceling each other out, the vertical poles for the chlorines and in and out poles for the hydrogens, nothing balances the overall rightward pole on the molecule that's combining between the chlorines and the hydrogens. And so the molecule has a fairly significant dipole, which we measure as 2.1. dBi is the unit. The final molecule, chloromethane, has a chlorine pole toward the right that's relatively significant. There is nothing balancing the chlorine's pole in any direction, so the molecule dipole ends up being more significant, even though it has fewer chlorines. The three hydrogens are all giving up some electron density toward the carbon and adding up kind of in the same direction as the chlorine, but most of their pull in the vertical and in and out planes, which is most of their pull, is balanced. So only a small amount of their already small bond dipole contributes to the overall molecular dipole. So this molecule's significant dipole of 2.3 dBi is really mostly about the chlorine not being balanced. There is a way to quantify polarity on individual bonds to calculate exact molecular dipoles. We're chemists, of course, we want to quantify it exactly. The basic idea is that the dipole of any individual bond, indicated by the Greek letter mu, is the product of the difference in charge, Q, and the bond length, R. If each one of these is calculated, one can use geometry to add all the vectors, we call them moments, together and give a molecular dipole. This is really only a reasonable computation in trivial cases. When we actually do this in real systems, we use complex molecular orbital calculations to calculate both the Q and the R values, and so the calculation of a molecular dipole is comparably trivial. And so those are usually done automatically by the same types of packages that calculate Q and R. For this class, we care a lot more about the qualitative approach that we just did, are the bonds polar, and if so, are they balanced, than we care about the actual quantification. Let's walk through a few more examples. While in theory, we could pull up an electronegativity chart for each of these problems, we'll use periodic trends to talk about relative electronegativity that can give us a general picture, especially since that's what's more readily available. Remember that further towards the right within a period is more electronegative, all the way up to the halogens, and further toward the top is more electronegative as well, for a maximum at fluorine. Hydrogen is less electronegative than carbon, even though it's in its own period, but it's similar enough that its bonds to carbon are not considered polar. So if you remember that hydrogen is between boron and carbon, and that we have the general trend increasing towards fluorine in the top right, that gets you most of the relative electronegativities fairly easily. Our first molecule is actually an ion, ammonium, NH4 positive. The four hydrogens are arranged tetrahedrally. Even though the ion carries an overall charge, and every one of its bonds is polar with the more electronegative nitrogen getting more electron density, the molecule itself does not have a dipole overall, because everything is balanced. The next example we'll talk about is azide. A few slides back, we showed that azide has three resonance forms, each giving a picture of the whole molecule based on their relative stability, and each having a linear geometry. Hopefully it's clear that nitrogen has the same electronegativity as itself, but the formal charges on atoms are also really important, and even more important than a partial dipole. In the top resonance form, there is a pull towards each negatively charged nitrogen. However, since the molecule is linear, the poles are balanced and there's no dipole in this resonance form. The next two examples each have a dipole, but since they are both equally stable pictures of the actual molecule, the overall molecule has no dipole. The next example is methanol, and is more similar to actual molecules we'd see in organic chemistry. The Lewis structure has three carbon-hydrogen bonds, which we can assume are mostly nonpolar, and an OH bond to a carbon as well. We call this type of molecule with an OH bond to a tetrahedral carbon an alcohol. The main two bonds of an alcohol that are polar are the OH bond, which pulls towards the oxygen since oxygen is further to the right in the period, and the CO bond, which also pulls towards oxygen for the same reason. Oxygen is far more electronegative than carbon and hydrogen. This means there's an overall positive on the carbon and hydrogen side of the molecule, with a little bit more positive on the hydrogen than the carbon. The oxygen is overall negative, so we see the net dipole shown in red. Every time we see this type of arrangement, even on longer molecules, this region of the molecule will carry a dipole towards the oxygen in the exact same way. Here are 3 more examples. First, try to predict the geometry of the molecule, and then try to predict whether or not the molecule will carry a dipole. Pause to do these, and then we'll go over them together. The first molecule is sulfur dioxide. It's really important to get the Lewis structure right, otherwise the geometry will be off for this molecule, and so will the polarity. It's tempting to draw the molecule linear, just like carbon dioxide, but the sulfur needs to have 1 lone pair in order to have the right number of electrons overall. There are 2 other resonance structures with a positive charge on the sulfur and negative charge on one or the other oxygen, but the resonance structure shown is the most stable, and both of those resonance structures balance out. In case you're skeptical, remember that sulfur can use its d orbitals to exceed an octet, so this is the most stable Lewis structure. In any case, there will be 3 groups, and the molecule will be trigonal planar overall, and bent if you're just talking about the atoms because it has 1 lone pair on the sulfur. Because oxygen is above sulfur in the periodic table, it's more electronegative. Each sulfur-oxygen bond will therefore have a dipole towards the oxygen, and we end up with a net dipole overall directly in between the 2 bonds, toward the oxygens with the more negative side and towards the sulfur with the more positive side. Notice again that this would not be true if we drew the sulfur dioxide linearly, because then the oxygens would be opposite each other and their pole would cancel out. So the geometry is essential to getting this problem right. The next molecule, formaldehyde, CH2O, has a relatively simple Lewis structure, which translates easily into a trigonal planar geometry. The carbon-hydrogen bonds can be ignored, but the oxygen is much more electronegative than the carbon, giving only 1 bond that's appreciably polar, which translates pretty directly into a molecular dipole. The final molecule, methane, is completely symmetrical with bonds that we consider nonpolar. It's nonpolar. So nonpolar.